Okay, so Carlos has already done a really good job actually of introducing Cyclone, but Cyclone is very much a big collaborative effort. It's primarily developed by the STFC Hartree Centre, which is sort of midway between Liverpool and Manchester in the UK. Rupert, myself, and Sergi all work there, but then there are also developers at the Met Office. So Eva, Chris, and Andrew have all contributed, and we have Jörg Henriks in the Australian Bureau of Meteorology, who has also contributed a lot. And both Eva and Jörg will be presenting on different aspects of Cyclone later on. So this is what I'm going to talk about now. So I'll just touch very briefly on motivation in case you missed Rupert's 3Ps talk earlier. And then obviously I'm going to talk about Cyclone, what it is, what it does, the two modes of operation that it has, and how that fits in with our view of levels of abstraction. And then having done that, I'm going to talk about the different domains that Cyclone targets. So we have three domains that we're going to cover in this training course. The first one, and our primary one, is Elfric, which is the Met Office's new atmosphere model that's being developed to replace the UM. And then I'll go on to talk about GOcean, which is more of a prototyping API that we use. And then finally, I'll talk about Nemo and how we are targeting Nemo with Cyclone. And I'll touch on a few other features that certainly Jörg will be picking up on during the training course. So motivation. So hopefully you saw Rupert's talk and you will be convinced that performance, portability and productivity are all good things, and ideally we would like our models to have all of those things to be able to perform well on whatever computer we have access to even work on that computer, and to be as straightforward and robust as possible when it comes to scientists developing software. And ideally we want that as single science source code, so single source science code, even, so that there's only one truth, if you like, and people are always working on that one truth. There's no chance of it splitting and people using a version that's no longer up to date. All of that kind of trouble is avoided. But unfortunately, we're in a world where you have complicated parallel code, you have complicated parallel computers, and they're getting more complicated all the time, and then you have complicated compilers. And all of that means you have a very complicated optimization space. And there's unlikely to be a single solution. In fact, there isn't going to be a single solution, I would argue, that works well everywhere. So the solution that we've adopted is to try and separate out the science specification code from the code optimization. So separate out the bit of code that does the science, as Carlos talked about with his MATLAB example, from how that is implemented, how you get good performance on a particular computer. So Cyclone. Cyclone is one possible way of tackling this problem. It is a domain-specific compiler for domain-specific languages that are embedded. So, and in our world, they are embedded in Fortran currently, although I'll say a little bit about that later. Cyclone is configurable. It supports finite difference type, finite volume type codes like Nemo, so existing code, and then it supports the GOcean API, which is also finite difference, but is a higher level representation. And then obviously we support the Elfric domain, which is finite elements, mixed finite elements. It's currently primarily targeting Fortran, so it takes in Fortran and it produces optimized Fortran, although we now have functionality where we can also produce OpenCL for the GOcean domain as well. It supports both distributed and shared memory parallelism. So certainly in Elfric, it supports putting in all the necessary Halo exchanges, that kind of thing, and it also supports OpenMP and OpenAC parallelization. And you'll get hands-on experience with all of those as you go through the training. So it has two modes. It supports code generation, so it takes some high-level description of the problem that you're trying to solve and generates the code for that from scratch. But we also support this idea of code transformation, which Carlos talked about a bit, where you have existing code such as Nemo and you want to transform it in some way. Cyclone is typically really aimed at HPC experts. So it's designed to be a tool that people can use to work around limitations or bugs, for instance. So often you might find that when you're trying to build a certain model on a certain machine with a certain compiler, you hit a particular problem, for instance, a bug in the compiler, and short of getting hold of a different version of the compiler, there's nothing you can do about that. So the idea of having a tool that is flexible is that it helps you work around limitations like that. The optimizations that Cyclone applies are provided to Cyclone as a recipe, as a Python script, rather than being baked into the scientific source code, so that when you move to a different machine, you can supply a different recipe to optimize the code in a different way. And ultimately, I think the bottom line is that Cyclone enables scriptable whole code optimization. So you can control the optimization of a whole code in this particular domain using Cyclone optimization scripts. The basic structure of Cyclone looks something like this. You'll see this diagram or variations of it a lot over the coming presentations. At the heart of Cyclone in the green ellipse is the Cyclone internal representation. And it's that all transformations work on. So when you apply a transformation in Cyclone, the transformation acts on that internal representation. And you might apply more than one transformation. You might apply different transformations depending on which computer you want to run on. And then once you've finished and you've done all the transformations you want, you then generate code out of the back. And normally that's Fortran, excuse me. But as you can see, there are other options. So we also support OpenCL in a limited case, and we also support mapping into other internal representations, which Rupert will talk about tomorrow. I think he's going to talk about that. On the left-hand side of this diagram, you have our front ends. So they're all Fortran based at the minute. So you can see in each of those front end boxes, there's a little box that says FParser, which is our Fortran parser. So the Fortran parser reads Fortran in, turns it into an abstract tree, and then we use that tree, we extract the information we need from that tree in whichever front end it is before we then generate the internal representation. So a little bit about FParser. FParser is a parser written purely in Python. It supports Fortran 2003 and some 2008. It's open source, it's on GitHub. We are actively developing it. It can, as of the moment, can fully parse the unified model, Elfric code and Nemo source code. There are still some outstanding issues that we need to work on in order to get it to parse the IFS model from ECMWF successfully. And it can be installed from pip, as shown there. And basically what you need to take away from this slide is that you start off with Fortran, as in the black box at the top, and FParser works on that and generates a parse tree shown down below here. And this is just a tree of Python objects. And you can, if you look at that, you can see you've got an execution part, and then that contains a do loop and so on. And that's very much a language specific representation of the code. And as I say, this underpins all of the front ends that we have in Cyclone at the minute. And there'll be a little tutorial shortly where you will get to play with FParser and have a look at the kind of information it produces. So there are two modes of operation, as Carlos mentioned, for Cyclone. There is revolution and there's evolution. So revolution was where Cyclone started. The idea is that the scientist writes a code from scratch in a DSL, and because the DSL is new, the code has to be new or moved over from whatever it's written in currently. And using that higher level representation of the problem, Cyclone will generate code for you. There are currently two domains that follow this model in Cyclone. There's the Elfric domain, which is by far and away the most advanced and the most complete, and that supports mixed finite elements on a mesh that is unstructured in the horizontal but structured in the vertical. So that means that to work out where you are on the mesh, you have to do a lookup. But once you've done that lookup, you can go up and down the vertical without having to do any further lookups. So you can get performance that way. And as a choice, it was chosen that Elfric would be, the DSL would be embedded in Fortran because that's what the Met Office developers are familiar with. So we have a domain-specific language embedded in Fortran. The GOcean API is very similar in that it too is a revolutionary approach, and it's a DSL that is also embedded in Fortran. But in this case, it targets a two-dimensional world doing finite difference operations on a fairly structured grid, albeit stretched. So it's a lot simpler than having mixed finite elements, and therefore we use it for a lot of our prototyping work, and Sergi will talk a bit about that later. and it enables us to do more rapid development to target sort of more esoteric architectures. So those are the two. That's where we started, really. That was Revolution. And then we tried applying that approach to other models and other domains, and other people said they weren't willing to rewrite their code, which is fair enough. It's taken, it might have taken decades to get to where they are. The idea of starting again from scratch doesn't appeal to everybody, or they can't afford it, quite simply. So out of that was born this idea of evolving an existing code. So it happens that certainly with code like Nemo, it follows very strict coding conventions. Most of the code is doing very similar stencil type operations, and therefore there is a way that you can process that code and recognize certain structures within it, and then from that, plus maybe some configuration information that you read in from files separately, you can construct a higher level internal representation of that code, and then that allows you to apply optimizations and transformations that a normal general purpose compiler cannot, because it doesn't have that domain specific information. And this approach is in development for the Nemo model plus associated components of Nemo. So for instance, the sea ice and the Medusa biogeochemical model. And Jörg has also experimented with applying it to the ROM's ocean model as well. So when talking about domain specific languages, it's common to think about the levels of abstraction. And there are 3 levels of abstraction that I'm going to talk about really during this talk. The bottom one is language specific. So this is where the FParser parse tree comes in. For instance, obviously it's parsing Fortran. The output you get from FParser is specific to Fortran. It contains things like do loops and whiles and all of that, and it's very much embedded in Fortran. Above that, we have the Cyclone internal representation, which is language independent. So it aims to provide a way of representing any procedural code such as C or Fortran or C++, but in a way that is language independent. And that then means you can map down to different language specific backends. And neither of those things are domain specific languages. They're just ways of programming a computer. Essentially, they're ways of providing instructions to a computer. Above them is where you have a domain specific language. So there you have maybe an internal representation that's specific to Elfric or specific to Nemo. And these things in Cyclone are built on top of the SciIR, and then you have Nemo specific subclasses of the SciIR, for instance. And that's where your domain specific information comes in. So I'm going to talk through these domains in a bit more detail now. I'm going to start off with the Elfric domain, which, just to remind you, is Revolution. So this is writing new code from scratch. And the approach taken in Elfric is called Cyclone, which stands for parallel system, kernel, and algorithm. So you have these 3 layers as illustrated here. The idea is that the science input, the natural science input, goes into the algorithm and into the kernel. So in the algorithm, you're dealing with what are logically whole fields. You're not worrying about whether how this field is split over the Earth, whether it's divided up into chunks, any of that doesn't matter in the algorithm. You're just dealing with a field, maybe horizontal wind velocity or something. In the kernel, you are actually providing a Fortran implementation of how you do the computation, a particular computation. So for instance, from Carlos's example, maybe something like a grad or some other stencil operation, you are actually implementing in the kernel how you do that. So you're operating on Fortran arrays, just plain arrays, and doing some mathematical operations. And you're doing that for just a single column of cells in Elfric most of the time. There's no information on parallelism in the kernel either. In fact, a requirement of a kernel is that it must be able to be executed in parallel with other kernels. So that means that between the algorithm, which deals with logically global fields, and the kernel, which deals with a single column of cells, there obviously has to be a layer that glues those two together, that knows about the fact that your field is in fact spread out over maybe many nodes of a supercomputer, and that it consists of many columns of cells. And so in there you will have loops over those cells, over those columns, and it will provide the necessary information down to the kernel. And in the domain of weather and climate, it's that work over a column of cells that is where you get your parallelism from. Obviously, you share out those columns between CPUs or GPUs. And that therefore is where most of the computational science, the optimization work goes in. So that means you naturally have these three layers. So the scientist writes an algorithm, and they write or provide kernels, and then Cyclone's job in this world is to generate that parallel system layer with all the necessary parallelism inside it. In terms of levels of abstraction, it looks like this. So we start at the top in the Elfric DSL. We have a relatively high level of abstraction where we have this specification of the algorithm, which says which kernels we're going to call. And each kernel has some metadata associated with it that describes what fields it accepts and what fields it provides back. And that information is used by Cyclone to generate an Elfric specific version of the Psi layer, of the SciIR, and it's that where transformations are applied. And once those transformations are complete, that maps down to generic SciIR, which then in turn maps down to generating, at the moment, parallel Fortran code, although of course other options might become available in the future and ideally will become available in the future. But I think Rupert will talk about that later. So to give you an example of what this looks like in code, this is the kind of Fortran that you would see in the algorithm layer. So you have these field objects. They're, as I said, they're global objects. And then those fields are supplied to kernels in an invoke. So an invoke is a special markup, if you like, that is used in the algorithm layer, and it's saying to Cyclone that I want to call these 4 kernels. I want to call setValC, scale matrix vector kernel type, blah, 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 and I'm going to pass these different fields to these different kernels. And this is saying to Cyclone that these kernels need to be called with this data. Please do it and make it parallel. And so when you run Cyclone on this, it generates code for you. But in order to generate that code, you need to know about the kernel metadata, or Cyclone needs to know about the kernel metadata. So for instance, this kernel apply variable hx kernel type takes a lot of arguments. Actually, it takes some fields, and in the metadata we specify which function space they're on and whether they're read or write, and then it takes some operators as well which map between function spaces, and which function spaces those are is listed on the right hand side as well. An important part of this metadata is that it specifies what this kernel iterates over. So this kernel iterates over cells, which means it expects to be provided with a single column of cells, and the loop that loops over all of those columns of cells must be generated in the Psi layer. So that Psi layer code, or a fragment of it, might look like this. So this is the code that Cyclone has generated. It's read the algorithm, so it knows what kernels need to be called with what fields, and it's read the kernel metadata, so it knows the details of those kernels, and then it's able to generate this code. So you can see at the top there is a loop that is setting the contents of grad p proxy to be 0, and then we have this loop over cells essentially here. No, that doesn't work. Loop over cells, and for each cell or column of cells we call this kernel, and you can see Cyclone has had to generate an awful lot of extra information in order to provide the sizes of various arrays and things into that kernel. And then below that there is another loop over cells, and we're calling a slightly simpler kernel with those arguments there. At the moment, there's no evidence of parallelism in here. This is just serial code. This is sort of vanilla Psi layer code that Cyclone will generate. In order to do optimizations on that code to target maybe different computers, then you need to apply transformations. So to do that, we're just going to walk you through a very simple example, which you can find in the Cyclone repository as example 3 in the Elfric directory. And in this example, it's very simple. There is just one kernel. So our invoke in this case calls a single kernel with those fields. The SciIR that for the Psi layer that Cyclone would generate for that invoke consists of, because there's a single kernel, you can see there's a single coded kernel down here, solver W3, and there's a loop up here over cells with an upper bound of n cells. So that's the SciIR that Cyclone constructs for this example. And then we want to transform it. And to transform it, I realise I've chosen rather a complicated version of the script here. You'll be pleased to know the examples in the tutorial are a lot simpler than this. But essentially, the interesting bit for our purposes is at the bottom here, where we loop over all the children in our schedule, and we say, is it a loop? And is it a loop over colours? If so, then we parallelize the loop inside the loop over colours. If it's not a loop over colours, then we can parallelize it straight off, and we apply this OTrans transformation, which we have previously constructed up here, and is a Dynamo 0.3 parallel loop transformation. Once you've applied that transformation, obviously the internal representation used by Cyclone changes, and you get a directive node added up here, like so. I can see I'm running through time really rather rapidly, so I need to get a move on. As well as generating the Scalar code, Cyclone also has to modify the algorithm there. So in the algorithm there, we had this call invoke. Call invoke is not standard Fortran. It won't execute. It should compile, but it won't execute. And therefore, Cyclone has to modify the algorithm there like so. So it's generated a call to this generated subroutine in the algorithm there. The GOcean domain is very similar to Elfric, except it uses a directly addressed arrays on a 2D mesh. So a kernel is now pointwise, so you pass in I and j to this kernel, and it knows that it's going to operate on the points I and j of the fields it's been provided with. The fact that it's a lot simpler means that it's a lot easier to implement other models in this and to implement other backends. So for instance, Sergi will be talking about the work he's been doing on generating OpenCL for this, and also work in progress on generating COCOS for this as well. The Nemo domain. So the Nemo domain, unlike Elfric starts at the top and goes down. Nemo starts at the bottom. So you start with existing Fortran code in Nemo. You parse it using FParser. From that parse tree that FParser constructs, we construct the Cyclone internal representation. And then from that, because we know this is Nemo, we can go up to a Nemo-specific internal representation, at which point we can apply transformations as we do in Elfric, and then generate code out again at the bottom. And at the minute, that's generating parallel Fortran. So that looks a bit like this. So there's other examples in Cyclone. So I've taken EG2 from the Nemo examples here, which is one of the tracer routines out of Nemo. And the original Fortran looks a bit like this. You've got an outer loop over tracer species, and then inside here you've got a lot of Fortran array operations, some initialization, and then some stencil operations. Cyclone can process that code and generate the equivalent Cyclone internal representation of it. And you can see here you've got a triply nested loop, and inside it you've got what we call an inline kernel. So because Nemo is written code, we treat it as though, for instance, the body of this triply nested loop here is a manually inlined kernel. So that's why it's called an inlined kernel in the Cyclone internal representation. Transformation scripts for Nemo look very similar to the ones for Elfric because they're also targeting the Cyclone internal representation, except that you might be making slightly different choices. So for instance, in this script, we're looking for loops that are over vertical levels. And if we find one, then we're applying this OpenMP transformation. Yeah, we're applying an OpenMP parallel loop transformation to the loop over vertical levels in this script. And then once you've done that, of course, the CIR is also transformed and you get this directive added. So you can see now you've got your OpenMP parallel do directive outside your triply nested loop with your inline kernel in the middle. And then when you generate Fortran, as you'd hope, you get, again, your triply nested loop, and you've now gained these OpenMP directives outside where Cyclone has worked out what should be private. So it's privatized over scalars. Other features that particularly Jörg is going to talk about is the PSI Data API. So that's a way of, it's called that because basically it's a way of getting data of any form out of the PSI layer. So if you think about that, that means essentially we're allowing you to insert calipers into the CIR and say, at these points, I want certain data to be pulled out, and that means you can then do profiling, you can add in extra stuff to do debugging, you can do validation, and you can extract kernels or a whole chunk of kernels in order to maybe create a standalone benchmark, for instance, or investigate some compiler bug that maybe you found. So that's all exciting stuff, and Jörg's going to be talking about that tomorrow, including a hands-on practical of doing various things. And the picture at the bottom of this slide is some profiling information out of Nemo that was added using the PSI Data API. So it's Nemo running on the GPU. And then, of course, there are other transformations that we will be going through in some detail in the various hands-on practicals. There's loop fusion you can do. There's OpenMP I've talked about here. There's OpenAC for targeting GPUs. There's OpenCL, which we haven't got any hands on because that's still under development, but Sergi will be talking about some more details to give you a flavor of what's going on there. And then there's a whole wealth of transformations related to how one might optimize Halo exchanges that Rupert is going to talk about tomorrow, I think. So in summary then, Cyclone is a domain-specific compiler for use with both domain-specific languages, so the Elfric type approach, and existing code, so the Nemo type approach. It's intended as a tool for use by an HPC expert. And I realized, having written these slides, that although that's true, and if you are writing transformation scripts and things, you will probably be an HPC expert, obviously it is also a tool for the science developer, because it means that they don't have to worry about parallelism and all of that stuff. They can just write the code that they want, and the details of making it run in parallel or run on a GPU are handled by Cyclone. So in a sense, it's a tool for the scientist, but it's only a tool in the meaning that it should make their lives easier. They shouldn't really have to know that they're using it. Cyclone is configurable, so as I've said, it supports both the Elfric and GOcean domains where one is writing a code from scratch, and we're also working on this approach of evolution, so taking existing code such as Nemo and constructing an internal representation of it, and then allowing the normal standard Cyclone transformations to be applied to that. The transformations, as I said, are provided by a user in the form of Python scripts, which you will get very familiar with over the hands-on sessions over the next couple of days. And those scripts transform that Cyclone internal representation. There is other functionality that we often don't talk about when we think about DSLs, but for instance, the PSI Data API in Cyclone makes error checking possible, and it also allows one to insert maybe visualization functionality to get data out, or I'm trying to think what I meant by analysis there. I think we'll stick with the visualization, that's good enough. And ultimately, at the end, it generates Fortran or OpenCL for GOcean of the transformed PSI, and then that Fortran is passed to a standard compiler. So thank you very much. There are user, developer, and reference guides available for Cyclone, all on Read the Docs at the address there. And if you have any questions, or please add them to the Google Docs document now, or bring them up in Slack, and we will do our best to answer them. Thank you.